binomial distribution is made up of binomial trials. A binomial trial is nothing more than a procedure that has only two outcomes. These two outcomes are generally labeled success and failure, true and false, or yes and no. A binomial trial could be something simple like tossing a coin, the two outcomes being heads or tails, or tossing a pair of dice, the outcomes being getting a 7 or not getting a 7. Even survey questions are binomial trials. Do you use brand X, or will you vote for candidate XYZ? Here the outcomes would be either a yes or no response. The point is that a binomial trial has only two outcomes. Let's set up some definitions before we discuss the binomial distribution. We will use lowercase p as the probability of success for each trial. We will use lowercase q to represent the probability of failure for each trial. Note, this is always equal to 1 minus p. We will use lowercase n for the number of trials in the distribution. Lowercase x will represent the number of successes in the n trials of the distribution. The probability of x is the probability of getting exactly x successes in n trials. How to make use of these definitions will become clearer when we use them in an upcoming simple example. Let's first note the characteristics of a binomial distribution. A binomial distribution has a fixed number of trials. If the number of trials changes, it becomes a different distribution. We will see what this means in the next video. The trials are independent, which means the outcome of any trial has no influence on the outcome of any other trial. Each trial has only two outcomes, as already discussed. The probability of success for each trial is the same. Now let's try a simple example. This example will be the tossing of 3 dice. Each die has 6 sides and are numbered 1 through 6. Each number has the same probability of appearing face up after being rolled. We will choose getting a 2 showing face up as our success. This means p will equal 1 over 6 because getting a 2 showing face up is 1 out of 6 possible outcomes when tossing a die. Q is therefore 5 over 6, and n is 3 because we will toss 3 dice. We have a fixed number of trials, 3 for the 3 dice. Each trial is independent. The outcome of tossing a die does not influence the toss of any other die. Each trial has only 2 outcomes, getting a 2 or not getting a 2. The probability of success is the same for each die, 1 over 6. Therefore, the tossing of 3 die meets the criteria of a binomial distribution. Each trial has 2 possible outcomes, 2 for the first toss, 2 for the second, and 2 for the third toss. According to the fundamental counting principle, there should be 2 times 2 times 2 equals 8 possible outcomes or permutations. A possible first permutation could be a 2 followed by a second 2 followed by a third 2. A second permutation could be getting a 2 followed by getting a second 2 followed by not getting a 2. The 2 with a bar over it indicates not 2, that is, some number other than 2 showing face up on the die. A third possible permutation could be getting a 2 followed by not getting a 2 followed by getting a 2. When all the permutations have been determined, we find that there are indeed 8. For the first permutation, we will determine the probability of getting a 2 and a 2 and a 2. To calculate this probability, we use the multiplication rule. That would be 1/6 times 1/6 times 1/6, which makes the probability of getting 3 2s equal to 1 over 2/16. The probability of getting a 2, followed by another 2, followed by not getting a 2, is 1/6 times 1/6 times 5/6, for a probability of 5 over 2/16. The probabilities of the remaining 6 permutations are calculated the same way, using the multiplication rule. Let's now determine the probabilities for each number of successes. There is only one permutation where we get 0 successes, and this is the case where all the outcomes are not a 2, which is equal to 125 over 216. There are 3 permutations where we have exactly one success, and they each have a probability of 25 over 216. Therefore, this permutation, or this permutation, or this permutation will result in an outcome of exactly one success. Using the addition rule, we find the probability of exactly one success to be 75 over 216. For the probability of exactly two successes, there are also three permutations, each having a probability of 5 over 216. This makes the probability of exactly two successes equal to 15 over 216. There is only one permutation where there are three successes, making the probability of exactly three successes equal to 1 over 216. It is these four probabilities that make up this binomial distribution. This is a graph of the binomial distribution we just studied. The values along the horizontal axis represent the number of successes, and the values on the vertical axis represent the probabilities. For example, the probability of 0 successes is 125 over 216, or approximately 0.5787. So the probability of 0 successes is 0.5787. We also determined that the probability of one success is 75 over 216, or 0.3472. The probability of getting exactly one success is 0.3472. The remaining values of 2 and 3 successes are likewise displayed on the graph. In the next video, we will develop an equation to express the probability of x in terms of p, the probability of success, q, the probability of failure, and n, the number of trials.